Hello my dear listeners. In this tutorial I continue from where I left in tutorial 1, that is foundations of design and analysis of algorithms. Okay, I will quickly recall the listener to the algorithm properties that were told in the previous deliberations, and algorithm properties, okay, that may be very few important properties, but there are subtle points about the algorithms. We will just make a recall about them. As examples befitting the nature of algorithms or satisfying the properties of certain algorithms, we look into three important algorithms of your Euclid's algorithm, consecutive integer checking algorithm, elementary school algorithm, all the algorithms meant for finding greatest common divisor of two integers. Then we will delve on Sieve of Eratosthenes, which is an algorithm of which was developed years ago during 276 BC, which will help us to list the prime numbers up to a given number. Okay, we will go one by one, stage by stage. Okay, a quick recall. Algorithm is a notion because all algorithms will be developed in the mental frame of the algorithmist. Okay, and algorithm cannot be executed directly by a machine. Therefore, algorithm is a notion. Non-ambiguity is a major requirement from the algorithm. Okay, and you cannot develop an algorithm for ambiguous problems or uncertain problems or vague problems. For example, you cannot develop an algorithm to lead a happy life, and you cannot develop an algorithm to prepare strong coffee. And the range of inputs is to be specified very carefully for every algorithm, because it is said that an algorithm would crash if inputs are chosen which are lesser than the lower bound of the input and input value is more than the upper bound of the input. Okay, the same algorithm can be represented in different ways, and you can choose flowchart, you can choose a pseudocode way of representation, or you can write an algorithm in the textual manner so that every step will be explained in using natural language. Several algorithms may exist for solving the same problem. The best example that we chose was the sorting problem. I told you there are more than 12 algorithms meant for sorting numbers, sorting names, sorting alphabets, whatever. Few examples are quick sort, merge sort, selection sort, bubble sort, radix sort, heap sort, like this. Okay, and algorithms for the same problem may be based on very different ideas. That means you can choose a strategy for designing the algorithm, the strategy that is well known to you. It could be a brute force method, it could be divide and conquer, it could be decrease and conquer, it could be transform and conquer, it could be a trade-off of the space against time, it could be dynamic programming style, or it could be greedy algorithms, as a matter of fact. Okay, as an example to substantiate the above listed points, that is the properties of the algorithms, we explain three algorithms which will stand as a befitting examples. Okay, three algorithms which are written to solve the same problem, the problem being finding the greatest common divisor of two integers. Okay, we discuss Euclid's algorithm, successive integer checking algorithm, elementary school procedure or elementary school algorithm. Okay, the Euclid algorithm, as the name itself would imply, it was devised somewhere around mid to 4th century BC by so-called father of geometry, the founder of geometry, okay, the Euclid. Okay, some of the topics that were listed in honor of Euclid has been Euclidean geometry, Euclid's elements, and Euclid's algorithm. Okay, Euclid's algorithm was developed to find greatest common divisor of two integers. here I will explain this algorithm in a step-by-step manner. GCD, the name of the algorithm. Okay, P is one integer, Q is another integer. Okay, the first step says if Q equal to 0, then return P as GCD and stop. Otherwise, go to step 2. Okay, if P is not equal to 0, if Q is not equal to 0, we have to proceed to step 2. Find the remainder S by dividing P by Q. Divide by P and Q, okay, P by Q, and whatever the remainder that you get is stored in S. Now, assign Q to P and S to Q. Okay, this is replaced by the Q in the second iteration, and this is replaced by P mod Q, whatever the remainder that remains upon dividing P and Q. Okay, assign Q to P and S to Q, go to step 1. Once again, this algorithm is repeated. Okay, so this algorithm can be succinctly represented as GCD PQ is equal to GCD of Q, that is the second one will come to the first place, and the second place will be occupied by P mod Q, the remainder upon dividing P by Q. Okay, is the algorithm, Euclid's algorithm, possesses all the properties? It is emphatic yes, because it clearly defines the bound of the inputs. Okay, it also states as to what is to be done if one of the inputs becomes 0. Okay, the inputs are clearly defined, there is no ambiguity about the inputs, and the algorithm eventually stops because you are successively dividing the number P by Q. Okay, P by Q, the P mod Q, somewhere at some point of time it should give you 1. It should give you 1 if both of them are, if P is not divisible by Q. Okay, it should give you at the end 1. If it is divisible by Q at some point of time, at some point of the iteration, it should return, this particular value will return 0, and this Q will be returned as the answer. Okay, so we will go through certain examples in order to reinforce our understanding in Euclid's algorithm. So the example is GCD of 124, 98. So we will go iteration by iteration. So 124 by 98. Okay, 98 will come to the first place, Q will come to the first place, and the second place is occupied by, second number is replaced by 124 mod 98. Okay, the remainder upon division of 124 by 98 happens to be 26. Okay, this will be the inputs for the second step. So GCD of 98, 26 is 26, Q will come to the first place, 98 mod 26. Okay, 98 mod 26 is equal to 20, therefore algorithm has to continue further. Okay, GCD 26, 20, there will be new inputs. Okay, GCD 20, the second input will come to the first place, 26 mod 20, 26 mod 20 will give us 6. Okay, in the next step 20 and 6 will be the inputs. Okay, 6 will come over here in the place of P, and 20 mod 6 will remain over here. It is 6, 2. Therefore, GCD of 6, 2 is GCD of 2, 6 mod 2. So Q will become 0, P is 2. Okay, Q will become 0, P equal to 2. Therefore, return 2 as GCD. Okay, so it has taken, though the numbers are quite big, 124, 98. And it required only 1, 2, 3, 4, 5 steps. So the algorithm never continues infinitely. So at some point of time, the second number should become either 0 or 1. Okay, it has to become 0. Okay, then we will return P as the answer. Right, and we will take the second example. Okay, the numbers are 55 and 17. GCD of 55 and 17 is GCD of 17, 55 mod 17. Okay, this is Q, P will become Q, and this is replaced by, okay, P mod Q. Okay, it will give you a GCD 17, 4, because 55 mod 17 is 4, and GCD 17, 4 will become the inputs for the second step or the second iteration, whatever you say. 4, 17 mod 4. Okay, it is GCD 4, 1, because 17 mod 4 is 1. The remainder after dividing 17 by 4 is 1. And once again, in the third step, GCD 4, 1. Okay, it will come with new inputs. So 1 will be placed over here. Okay, P will become Q, and this will become 4 mod 1. 4 mod 1 is 0. So when q becomes 0, you have to return p as the answer, returns 1 as GCD. Okay. Then the other algorithm is, second algorithm is consecutive integer checking algorithm. So therefore this is a pointer for us to tell that a single problem can have many algorithms. So here the problem is finding GCD of two numbers, okay, and we have two listed algorithms, okay, consecutive integer checking algorithm. It goes like this. Step 1 is find minimum value among p and q. Okay, find the minimum value of p and q and assign it to r. Okay, find in the first step itself, find the minimum of p and q and assign it to r. That is r equal to minimum of p comma q. Next, second step is divide p by r. If remainder is 0, go to step 3. Otherwise, go to step 4. So if the remainder becomes 0, we will be going to the step 3. There we will divide q also, other number also, by r. If the remainder is again 0, then return the value of r itself as the GCD. Otherwise, we will go to step number 4. In step number 4, which happens to be the last step, we will reduce the value of r by 1. Okay, we will reduce the r. Okay, we will reduce the r value of the r by 1. Okay, the minimum value among two numbers by 1 in the first iteration. Then we will once again go for step 2. Therefore, if the r, the minimum value to start with, will go on reducing 1 by 1 by 1, okay, only by 1, okay, till this r becomes a divisor of the original numbers. Okay, will completely divide two numbers. Otherwise, it has to divide both the numbers when it becomes 1. Okay, that is the thing. A careful analysis of the second algorithm would reveal that it doesn't work when one of the inputs is 0. Therefore, inputs are not clearly defined over here. Okay, in that case, p equal to 0. Okay, when q becomes equal to 0, when we try to divide p by q, it will result in infinity. Okay, this is the lacuna of this algorithm. And more than anything, if q will not divide this p equally, okay, then we have to go on reducing the value of q, or the value of minimum number, the value of the minimum value among p and q, till it becomes 1. Okay, if the minimum value is 50, we need to proceed for 50 steps. Therefore, this algorithm consumes a lot more number of steps when compared to Euclid's algorithm. And here inputs are not defined properly. That is another lacuna. Okay, we will take once again we will take two examples to illustrate as to how consecutive integer checking algorithm works. Okay, GCD 12498. Okay, the minimum among 124 and 98 is 98. It will not divide 124. Therefore, we will reduce r equal to r minus 1. It becomes 97. With r equal to 97, it will divide none of the numbers. Okay, it will neither divide 124 nor 98. Therefore, once again it is reduced to 1. Okay, reduced by 1, it becomes 96. It becomes 95. Okay, when it reduces to 2, when r becomes equal to 2, it will divide both 124 and 98. You can see over here. Okay, therefore GCD equal to 2. So it literally took, okay, 198 minus 2, 96, okay, and we have considered 98 also to begin with. Therefore, this algorithm takes 97 iterations, right? Okay, this is the second example, 755 and 17. A careful attention to these two numbers, a little consideration will show that 17 cannot divide 755. Okay, therefore we should go on reducing this 17 till let us see how long we have to reduce this one. Okay, 755 comma 17, the minimum value among them is 17. It will not divide 755, therefore we will reduce it by 1, 16. Once again, r equal to 16, it will never divide, neither divide 755 nor 17. Therefore, r equal to r minus 1, it becomes 15, it becomes 14. Okay, when it becomes 1, when r value becomes 1, it will divide both 755 and 17 equally. That means the remainder of division by 1 up to the two numbers 755 and 17 will yield us 0. Therefore, GCD value equal to 1. Therefore, it exactly took 17 iterations for finding the solution. Okay. The third one is elementary school algorithm, and we need not have to go to elementary school again. Okay, it is given in order to recall our memory, in order to recall our nostalgia of how we taught of finding GCD when we were in school. Okay, when we were in middle school, let us say. Okay, it goes like this: elementary school algorithm, GCD P comma Q, generate a list of prime factors of P. Prime factors of P. Once again, generate a list of prime factors of Q. List common prime factors among the prime factors of both P and Q. Okay, P would have given you a set of prime factors, Q would have given you a set of prime factors. Among the prime factors of P and among the prime factors of Q, just list only common prime factors. Okay, common prime factors. Find the product of the common prime factors and return this as GCD. Okay. In this example, in this algorithm, let us investigate the properties satisfied by this algorithm. Anyway, the one common property that it has satisfied is this is also one among the algorithms to solve the same problem. The same problem is finding GCD. Okay, the first two steps are ambiguous. Okay, it will raise a question as to how we can find the list of prime factors. How to find list of prime factors of P and how to find a list of prime factors for Q. So an algorithmist or a problem solver will be left to some kind of a dilemma. Okay, because finding a list of prime factors for a given number itself is an algorithm. Okay, we find an algorithm inside another algorithm. Okay, and this algorithm has not been clearly defined, therefore there is an ambiguity point. There is an ambiguity factor in this particular algorithm. The ambiguity is about finding prime factors of M and N. What is the method? That question arises. Okay, and this is the method of finding. Okay, this is the primary school method. So we were taught in primary school as to how we can find GCD of two numbers. Okay, and 98 is admitted. It is divided by the least prime number, that is 2. Okay, 2 49s are 98. Okay, further we cannot divide this 49 because it is a prime number. So prime factors are 2 comma 49. We have a list of prime factors for 98. In the same token, we will find the prime factors of 124. 124 is divided by 2, 62. Okay, 62 is divided once again factored by 2, it will give us 31. So it is 2, 2, 31. No more continuation because 31 is a prime number. Therefore, we will list the prime factors of 124 to be 2, 2 and 31. Okay, the common prime factor in the list in both the list happens to be 2 and 2. Okay, there is no other combination for 2 here, and there is no combination for 31 over here, neither there is a combination for 49 over here. Therefore, we will choose only 2, okay, from this pair. Therefore, the GCD is 2. Then we will go to another problem, that is 60 comma 80. The inputs are 60 comma 80. So prime factors of 60 are, divide it by 2. This is the first prime factor, 230. 2 30s are 60. Once again divide 30 by 2. It will give us 15. So 2 15s are 30. Once again we make use of 3, another prime factor of 15. 3 5s are 15. No more further continuation. Okay, therefore we will list the prime factors of 60 to be 2, 2, 3, comma 5. So there are 4 prime factors. In the same token, we will continue to continue solving this problem, okay, by dividing 80, by finding the prime factors of 80. So 2 40s are 80, 2 20s are 40, 2 10s are 20 and 2 5s are 10. No more further going. So here we got 5 prime factors. Here we have got 4 prime factors. Okay, 2 2 2 5. There is a pair of 2 and 2, one pair. The second pair, there is no pair for 3. There is a pair for 5. Okay, we find a pair of 2s, another pair of 2s and another pair of 5s. Okay, the remaining 2 has not found a pattern. Okay, not found a another 2 over here. Therefore, the number of 2s exhausts for only 2. Okay, there are 2 2s and 1 5. Therefore multiply 2 and 2 and 5, 2 into 2 into 5 will give us 20. Okay, so for the sake of completeness, we will discuss Sieve of Eratosthenes, which was found somewhere during 276 BC, during the time of the king Eratosthenes of Cyrene. He was a Greek polymath, a mathematician, a geographer, a poet, an astronomer, and a music theorist. He was a man of learning, after becoming the chief librarian at the Library of Alexandria. This is what history has to say about Eratosthenes. His famous contribution is listing prime numbers up to a given number, making a list of prime numbers up to a given number. Okay, it uses the concept of sieve. You have seen the sieves. Okay, it will come with different apertures. Okay, apertures, it is used anywhere things are to be sieved. Okay, here the numbers up to a given number will be sieved. So what remains in the top sieve is the prime numbers, a list of prime numbers, the prime numbers up to a given number. Okay, to execute this algorithm, okay, and we need to list all the numbers up to the given number. Let us say the given number is 25, therefore we will list starting from 2, because we cannot start from 1. 1 divides every other number, therefore 1 cannot be taken as a prime number. Okay, 2 is the universal prime number. Okay, so 2, 3, 4, 5 like this up to 25 we have listed, and once again we will start dividing, we will start making use of 2 to find out any other number in the list gets divided by 2. Okay, whether 2 to be told otherwise, we will be finding are there 2 can become a factor of any of the numbers. Okay, up to 25. So 4 goes, 6 goes, 8 goes, 10 goes, 12, 14, 16, 18, 20, 22 and 24, because they are all divisible by 2. Okay, they will pass through the sieve. So okay, what remains in the sieve is 2, 3, 5, 7, 9, 11, 13, 15, 17, 19, 21, 23 and 25. Now 3 will be chosen. 3 is chosen. Okay, whatever the number for which 3 is a factor is removed. Okay, here 15 goes, okay, because 3 5s are 15. Okay, and 21 goes, right. So what remains in the next cycle is 2, 3, 5, 7, 11, 13, 15 should go. Okay, it is marked as green. 17 will remain, 19 will remain, 23, and okay, when 5 is chosen, this will also go. Okay, right. Then 2, 3, 5. When 7 is chosen, there will be no other number that will be left. Okay, so none of the numbers is divisible by 7. Once again we will try with 11. Okay, no numbers are available. 13, no other numbers are divisible by 13. 17, like this we will end up with 23. Okay, it is shown in this particular line. Therefore the list of primes up to 25 is 2, 3, 5, 7, 11, 13. Okay, 11, 13, 17, 19 and 23, which will remain in this top sieve. Okay, we will end up this discussion with this. Okay, next to follow is tutorial 3, where we will discuss very important aspects of the algorithms. Until then, thank you.